Hi, it's time for another math easy solution. Today I'm going to go over further into infinite sequences and series, and now look at multiplication and division of power series, and look at this, go in depth in it. In my earlier video I went over an example on it, but I did not go over the proof as to why, and that is what I'll be doing here. So like always, you could if you don't have time to watch the whole video, you could play this video at a faster speed, and here's my recommendations, and it's a pretty amazing life hack. Your brain gets used to faster speed. Also, you could download and read the notes, on the Hive blockchain. I'll put the links to both in the description below. And also you could watch the video in parts, and I'll include timestamps of all parts in the description as well. So you can jump to whichever section you want to watch, including skipping this introduction if you don't want to hear this part. But anyways, let's just jump right in. So calculus book reference, note that I mainly follow along the following calculus book, and this one here is a Calculus Early Transcendental 6th edition by James Stewart. And let's just look at the topics to cover now. So recap on power series, Taylor and Maclaurin series, and then recap on my earlier example on multiplication and division of power series. And then I'll look at multiplication of power series, go over the proof, and look at example 1, which involves this power series, or this function e to the x divided by 1 minus x, and this turns out to be a multiplication of power series. And also example 2, go over that, which is sine squared of x. And then division of power series, this example 3, we'll look at that, which is hyperbolic, this is hyperbolic cosecant, or I'm not sure to pronounce that exactly. So yeah, I'll just be calling it hyperbolic cosecant. So CSCH x. Imaginary numbers, and in this example I'll be also discussing imaginary numbers and Euler's identity, and then double checking our result of division by using multiplication. So double checking division by multiplication, which is pretty fascinating when you think about it. So anyways, let's jump right ahead. So recap on power series. So here's a recap, or a quick recap of power series, which are a specific type of series. Again, a series is just a summation of a sequence. So here I just jump right in from my earlier video. More generally, a series of the form summation from n equals 0 to infinity of Cn times x minus a to the power of n, where this Cn are the constants, or called coefficients of the series, and then we have this integer, this n is going to be always positive integer. It goes from 0 to 1, 2, 3 all the way to infinity, and we're going to write this as C0 plus C1 times x minus a plus C2 times x minus a squared, and so on. And this is called a power series in x minus a, or a power series centered at a, or a power series about a. Notice that in writing out the terms corresponding to n equals 0, equations 1 and 2, and this one's 2, we have adopted the convention that x minus a to the power of 0 equals to 1. That's why we get rid of it, equals to 1, even when x equals to a, because you'll have a 0 to the power of 0, which is undefined, but here we're defining it using this convention, equals to 1. Notice also that when x equals to a, all the terms are 0 for n is greater than or equal to 1. So this all goes to 0. Yeah, so when it's plug in 1, they all vanish, and you're just left with this one based on our convention. And so the power series always converges when x is equal to a. Yeah, so when you plug in x equals to a, they all vanish except the first term, and that's just convergent. And here's a theorem as well here. So for a given power series, summation from n equals 0 to infinity of Cn times x minus a to the power of n, there are only 3 possibilities. The series either converges converges only when x equals to a, so that's always a possibility. I mean, that's always the case. The series converges for all x, or there is a positive number, capital R, such that the series converges if x minus a is less than r, the absolute value of x minus a, so this interval, and diverges if it's greater than this radius of convergence r. So if absolute value of x minus a is greater than r. And this r is called the radius of convergence, and the interval of convergence is the interval that consists of all values of x for which a series converges. Also note that in this case we'll call this r equals 0. This is termed r equals to infinity. And this one is just r. And in the case right here, the interval of convergence, this one is just equals to x equals to a, just a single point a. In this one here, the interval of convergence is going to be from negative infinity to infinity, And in the final one, you could write this, rewrite this inequality as this inequality, so a minus r is less than x, less than a plus r. And then, but the endpoints right here, a minus r and a plus r, when x is an endpoint of the interval, that is x equals a plus or minus r. Anything can happen, so this doesn't tell us if it converges or not at the endpoints. So we'll have to do that manually, so it could converge or diverge. So that we're gonna have 4 cases where it's open interval right here. This endpoints don't converge. This one right here, close bracket on the right, which is converges on the right, or close on the left, converges on the left, or close bracket both converges at both endpoints, and so on. And here's an illustration. So convergence inside here, within this radius is convergence, and divergence outside. And then here's put a circle there without filled because it could converge or diverge. But here, this one here, it's going to be filled because it's always convergent at A. Anyways, keep going further. To recap on Taylor and Maclaurin series, recall that the Taylor series is just a power series in which the coefficients are determined from the function's derivatives. So if f has a power series representation or expansion at A, that is, we have it right here, f of x equals to this, where our radius convergence is x minus a, again less than the radius convergence r. Then its coefficients are given by this formula, Cn equals to the nth derivative at a divided by n factorial. And remember, I went over proof in this video or in this earlier video on it. And then Taylor series of the function f at a or about a or centered at a, you could expand this all out, and it's going to be equal to like this. So expand this all out, plug this this Cn inside there, the Taylor coefficients, and we get this fa plus f prime of a divided by 1 factorial times x minus a, and it goes to 2 factorial, 3, and then the second derivative, third derivative, and so on. And Maclaurin series is just a Taylor series, but with a equals to 0. So just plug in a equals 0, we get the nth derivative at 0, and then this x minus a becomes just x, like that. Alright, so let's take a look at this recap on my earlier example on multiplication and division of power series, and that's the motivation for making this video. So recall from my earlier video on Taylor and Maclaurin series in which I went over the example of dividing and multiplying power series just as we would for polynomials. And here's from my earlier video on infinite sequences and series, Taylor and Maclaurin series. Actually, this is the same link as over here. This one's actually more updated, so I'll just remove this archive and retrieved. Alright. Yeah, so this is the same link there, so I'll just leave this, leave that date and the archive link. So anyways, multiplication and division of power series. So if power series are added or subtracted, they behave like polynomials, and this is theorem 11.28 shows this, and I'll reference the theorem below here. In fact, as the following example illustrates, they can also be multiplied and divided like polynomials, and we find only the first few terms because the calculations for the later terms become tedious, and the initial terms are the most important ones. So here's a theorem is referenced below that mentioned in the earlier video. So here, theorem 11.2.8, that's this one here, theorem 8 there. So if we have the series an and bn are convergent series, then so are the series c times an, where c is a constant, and the series an plus bn and an minus bn, and then we have, you could just take out the constant just as you would with any polynomial, and you could multiply it inside, etc. And when you're adding these two series, you can just separate them like any other polynomial. In other words, you could just do term by term adding or subtracting here. And note that polynomials and their terminology are referenced from my earlier video below. So polynomials is called a polynomial if p of x equals to an times x and then plus an minus 1 times x n minus 1. And this goes all the way to a0. And in fact, this is just reverse of the power series. In general, yeah, this is just the power series, but it doesn't go to infinity, and some parts, yeah, so you'll have, yeah, some parts 0 or whatnot, the coefficient 0. But anyways, this is just the power series, but it doesn't go to infinity. And yeah, there's a0, and then the x0 is going to be equal to 1, and then we have x, and then this is a1, and a2, x squared. This just goes this way, like that. And where n is a non-negative integer, and the numbers a0, a1, a2, all the way to an are constants called the coefficients of the polynomial, or similar to the coefficients of the power series. And the domain is infinity, because you could put any x value inside. So the domain is the set of all real numbers, so negative infinity to infinity. If the leading coefficient an, which is not equal to 0 here, then the degree of the polynomial is n. For example, the function like this, the highest power, the leading one, so this is why I put this n there, or leading, or the biggest one, is just going to be 6, like that. So that's a degree 6. And a degree 1 is, we'll just have a linear function, which is mx plus b. So it's a linear function, and a polynomial of degree 2 is a form of this one, ax squared, and it's called a quadratic function. Its graph is always a parabola, and yeah, so just a parabola there. And it opens upwards if a equals 0 and downwards if a equals to, if a is less than 0. And upwards if a is greater than 0. So yes, positive or negative. So anyways, back to the example on multiplication and division of power series. So we're going to look at the first 3 terms of this these examples. So example 12, find the first 3 non-zero terms in a Maclaurin series for a, e to the x times sine x, and b, tan of x. Yeah, for the first one here, for a, use the Maclaurin series for ex and sine x in table 1, and I'll get to that table later in this video. But here's the 2 series that we get. So e to the x, we already solved earlier that it was this in my earlier video. And then the sine of x is, this is the power series. So we can multiply these together. We multiply these expressions, collecting like terms, just as for polynomials. So here's this series multiplied by this here. We just lined up, or they just lined up the screenshot from my calculus book, just because it's just typed out, as opposed to my handwritten ones in the link there. But anyways, what they've done here is, so you have this multiplied by this, and in other words, they multiply each term. You just FOIL it out just as you would with polynomials. Multiply this by this. So x times 1 is going to be x, like that. X times x divided by 1 factorial, that's just going to be x squared, like this. And then x times x squared divided by 2 factorial, that's just 2. So this is going to be x cubed over 2. So you multiply the same thing over and over. Next one's going to be x to the 4. 3 factorials, 3 times 2 is 6. So we get this one right there. And then we do the same thing for infinite terms, and then we also go the same thing with this one here. So x, negative x3 divided by 3 factorial, that's divided by 6, times it by 1, that just becomes negative 1, negative 1x cubed, and then you multiply by this one, you get this x4, etc. Then you just add up all the terms. Can be x, this x squared, this one adds up to over here, and the next one adds up, etc. But the first 3 terms are that. And this is all just a FOIL method, so we get this answer, and I'll just scroll down to recall the FOIL method for multiplying polynomials. So proof, this is my earlier video, proof and simple alternative method. So basically the FOIL method is if you have x plus 3 as a polynomial with a degree 1, as a linear function, times x plus 5, so you multiply this x inside every single term, and then you multiply 3 into every single term. So we get this x squared plus 5x, then plus 3x, and then we get a 3 times 5, 15, and you add them all up. Yeah, so that is exactly what we did here. So that is all that we are doing here, multiplying this out. So we're just folding it as if they're polynomials, and in fact, it pretty much is a polynomial, but just goes to infinity. Now for part B was tan of x. So tan of x, using the Maclaurin series in table 1 we have, so we were given sine of x and cos of x power series, and we could divide these out, and we can use a procedure like polynomial long division. So we put the numerator in here. This is numerator. Is this part right there, and then we are going to be dividing it out by the denominator, 1 minus 1/2 x squared. This one is 4 factorial is 24, and so on. And then we'd be doing the same thing. So we have to find a number, multiply this by this to get this one here. So we just do an x. So x times 1 is 1. X times 1 is x. And then we have this one, then you just multiply every single one. It's going to be negative 1/2 x cubed, and it's going to be plus 1 over 24x to the power of 5, the x times 4 times x. And then you would just subtract. So this would cancel there, 0 plus this part right here. And then we'd find another number, this one times 1, times that by 1. That's going to be 1 over 3x cubed. And the reason we're doing that is just so that this part right here cancels. Yeah, so we get this one to line up with this. So we multiply whatever this is to match up this, and then we subtract, and then this goes to 0, and we keep doing that, and we keep going on. So this is just polynomial long division. And then we keep going on and on. So we get this one here, 2 over 15 times x5. That's because we have to get rid of this one, so we multiply that by 1. And then there is our term, is just this top part is the terms, and this is just polynomial long division. And here I'll just scroll down from my earlier video. So recall the concept of polynomial long division, which I explained in one of my earliest videos ever, including even the FOIL method is one of the earliest ones ever. You could tell by how the notes were not as neat as my later ones. And yeah, so we have polynomial long division. So if we have x squared minus 9x minus 10 divided by x plus 1, we could just do polynomial long division. So we have x here, x times x equals x squared. So this lines up and the equals 0 then. So when you subtract it equals 0. And then when we have the next one is going to be, yeah, so just multiply this all out. So x times 1. X, and then subtract this 9x minus 1x is 10x. The next one's going to be, well, 10. Negative 10. Negative 10 times x is negative 10x, and so on. So that's just polynomial long division. And then eventually, yeah, once we get 0, this can be 0 remainder. And so on has 0 remainder. So this divided by x plus 1 equals to x minus 10. So yeah, this was a polynomial long division, but here's copied and pasted more of the notes earlier just to drive home the point and illustrate further division. So this was right here. So x squared minus 9x minus 10 divided by x plus 1. We could also factor this out by finding two simpler polynomials that multiply together. That becomes this x squared minus 9x minus 10. So we could so it's going to be x minus 10 times x plus 1, and this could FOIL this out exactly as our FOIL method above here. FOIL it out, and we get this x squared minus 9x minus 10, and that's exactly this one. So we could just put this here, and they can cancel. This x plus 1 cancels with x plus 1. We get this x minus 10. So yes, we use the multiplication to confirm the division. And yeah, this x minus 10, you could use a polynomial long division and to solve the exact same thing. So anyways, keep going, scroll back up and read this again, the last part of the note. So we get, you could do polynomial long division or like it for procedure like long division, which is a polynomial long division, but for infinite power series, so infinite series or power series, right that. So right here, it says here, although we have not attempted to justify the formal manipulations used in example 12, they are legitimate. There is a theorem which states that if both f of x equals to the series Cn times xn, or the summation Cn times xn, and g of x equals to the series Bn times xn, and they both converge for absolute value of x less than r, and the series are multiplied as if they were polynomials, and the resulting series also converges for x is less than capital R and represents f of x, g of x. And for division, we require that b0 or b naught, the first term of the series that you're dividing by. So that's this g of x right there. So you have to, because if you have f of x divided by g of x, then the first term can't equal 0, and the resulting series converges for sufficiently small absolute value of x. And the reason is because, and as I'll get to later in this video, is you're going to be dividing by g of x. You have to ensure that there's no scenario where this is equal to 0, or any of the terms are equal to 0. So you have to make sure, yeah, none of them are equal to 0. Otherwise, you're going to be dividing by 0, which is undefined. You're going to get infinity, and so on. That's why it's got to be sufficiently small absolute value of x interval over there. And this statement is for Maclaurin series, but I'll be going over for general Taylor series derivation. Anyways, let's keep going further. Now let's look at multiplication of power series. So the proof that I'll be going over for multiplying power series, just as we would polynomials, is from the following lecture by Dan Slaughter from Furman University in South Carolina, USA. This is a lecture from actually 2004, so a long way back. This math course that I just found online, and it's in a PDF format. So multiplication and division of power series, Dan Slaughter, Furman University, Mathematics 39. If you happen to have been in this class or know this person, just let me know in the comments. Would be pretty interesting nonetheless. So anyways, MES note this lecture uses the variable z, but I'll be using the more common one, x, in this video, and also because I've been using x in the previous power series videos. So suppose that f of x and g of x are power series of the form, and let's write this one as here, f of x is equal to the summation up to infinity from n equals to 0 starting, and then we'll have an as our coefficients, and I'm going to call this x minus, I'll just call this x0 or x naught. Instead of our a, this is going to be x0, because we have an a right there, so an. And let's say we have, I'll make this a bit neater, x, and let's put a g of x, like that, equals to summation up to infinity, n equals 0, and call these coefficients bn. So it's just a power series, both of them power series, just different coefficients. X minus x0, and then this can be xn. And let's say both of these have radius of convergence of r. They both have the same one, as this is going to be x minus x0, and this can be less than the radius of convergence r. Yeah, so since both functions have a radius of convergence r, then the multiplication f of x and f of x times g of x can also be written as a power series with radius of convergence r. In other words, they both converge, so if you're multiplying a convergent series by another convergent series, you're going to get, well, the value times another value, they're both convergent. The multiplication is going to be convergent as well. So let's write our multiplication as another power series. So f of x times g of x equals 2 summation up to infinity n equals to 0, and I'll call this Cn like that. Yeah, so we have our a coefficients, b coefficients, and then we have a c coefficients for this one, and they're all just power series with different coefficients. So x minus x0 power of n, and this is going to be 4 x minus x0 is the radius of convergence is going to be less than r, like that. Alright, now for this function, we can write this as a Taylor series by first determining the Taylor coefficients, and let's just scroll up to the Taylor coefficients. Again, remember, Taylor series is just a power series where we can determine the coefficients, and you can solve them using the derivative. So Cn over here, the coefficients are equal to the nth derivative at a divided by n factorial. So in our case, we're going to have f times g, so we can write it in this format. So we'll have the coefficients c sub n is equal to, let's put our factorial first, 1 over n factorial, like that. And then times it by the nth derivative, and I'm going to write it as like this, so d over dn, this can be dxn, this is the nth derivative, and I'll put this as at x is equal to x naught, or x, x0, like that. In the definition we had at x equals a. But anyway, so we have x equals x naught, and we're going to write this as f of x times g of x, like that. And yeah, so write it in this format, and the reason we're not writing in the other format is because the other one had the fn of x, but since we're dealing with two of them, we can't just do this. This looks like this is a multiplication of two derivatives, so we can't just do that. So I'll just put this in a slight bracket. I thought it was important to note that. Alright, now note that this derivative is just a Leibniz rule, or the general product rule for derivatives, which I reference from my earlier videos below. But first, let's put this here. I'm going to put this is the Leibniz rule. This is, let's keep moving more space, writing. This is the Leibniz rule for the product rule of derivatives, for the general one, so the nth derivative, Leibniz rule. And yeah, this is the one I proved in my earlier video, or just a very recent video on the product rule, general product rule. So here's from my earlier video. This is from the product rule from a while ago. And so if f and g are both differentiable, then the derivative, you could write this as a derivative of f of x times g of x equals to f times the derivative of g of x plus g times the derivative of f of x. So you just alternate the derivative and the regular function. Like that. You could write it in many different ways, or you write it like this with the bracket number inside. And the general product rule is called the Leibniz rule, and here's from my earlier video, and this is a screenshot of it because I just put in the whole rule. So we have the derivative, the nth derivative. So this is just the general for the nth derivative. This is just the first derivative, is just the normal product rule, and then the nth derivative of f of x, g of x, f of x times g of x is equal to the summation k equals 0 up to n of this n choose k. Then you could write this in this is the n minus kth derivative of f times the times the kth derivative of g. And yeah, so it's a giant summation, but you could also write it in this way: the kth derivative of f times the n minus k derivative of g. And where n choose k, this is the binomial coefficient, this equals n factorial divided by k factorial, divided by n minus k factorial, like that. And the one that I'll be using is this one right here. That's just the one that the lecture PDF uses, but it doesn't matter which one you use, because remember here, if you look at the first derivative, you have this first derivative, and then it goes to the 0. So you have the first derivative of f, it goes to the 0th derivative, but you can just move this over to the other side so that you'll start with the g as the first derivative and goes to 0. And then the other one goes opposite. So you have the 0th derivative goes to the opposite, and that's just basically what this says. When you have k equals 0, that's the 0th derivative, and then this one will be the nth derivative. But otherwise, if you have it in this case, you'll have the nth derivative, and then g is the 0th derivative. And then note that the term n choose k, or n choose, this term n over k, or it's usually called n choose k, is a binomial coefficient, and the term binomial is just a polynomial with two terms, and it comes from this one here. So if you have x plus y to the power of anything, any integer, for example 4, you're going to have it x4 plus 4x3 y, and then and so on. So the coefficients in front, so this is n choose 0, then you have n choose 1, then you have n choose 2, and choose all the way to the end, n choose n. And for n equals to 4, you have it equals to 1, 4, 6, 4, 1. And also note the powers, you have x to the power 4, x to the power 3 goes down, 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 until you have x to the power 0. And then likewise, you have y to the power 0 goes up. So y1, y2, y3. But then you can move it over to the other side, so then you can start off with y to the power 4 and x to the power 0, and you can go up. So it doesn't matter, you're just rearranging where it is. And going further, just a more recap on the binomial coefficient. The binomial coefficient can be determined in factorial form, as shown here, or this one right here, or via Pascal's triangle, in which each entry is the sum of the two above it. So you could scroll onto this. This is Pascal's triangle. So you have 1. You start off with 1. That's the first coefficient. Is just going to be 1. For example, here's 1. So 1. Then you'll have a 1, 1. Yeah. So for this one is this is the 0th derivative. Is just going to be just the function. This one's going to be the first derivative. It's going to be 1, 1. Then notice that you could add up the ones above it. So the ones on the side, this one's 0 plus 1 just goes to 1. This one here, 1 plus 1 is 2. And then you get 1 plus 2 is 3. 1 plus 3 is 4, etc. And this is n equals 4, or the fourth derivative. So at this point right here, 1, 4, 6, 4, 1. Notice here, 3 plus 1 is 4, 3 plus 3 is 6. And that's just this one here, 1, 4, 6, 4, 1. So anyways, that was just a quick recap. So now we can write our Taylor coefficients as follows, and we're going to be using this notation right there, or that convention. So let's just scroll up to our coefficients right here. So we have Cn equals 1 over n factorial times the derivative, which is just the Leibniz rule of these products, at x is equal to x naught or x0. So let's just write this down. So we'll have Cn is equal to 1 over n factorial. And let's just write the full derivative first. D over, this is the nth derivative. This one's going to be n at x equals to x naught or x0. This is f of x, g of x. So now this is going to be as a summation. This equals to 1 over n factorial. Summation up to n for the nth derivative. And this is going to be k equals to 0. This is n choose k. And then it's going to be the f of kth derivative of x. And then the next one's going to be g of n minus k of x, like that derivative. So that's the n minus kth derivative of g of x, like that. And then let's just double check we got this all correct. So yeah, this one right here, n choose k is from k equals 0 to n. And then you have a kth derivative of f, and then times the n minus kth derivative of g. So yeah, this looks all right. And now we can just replace this n choose k with our formula. And I might prove this formula in a future video. But anyways, this is going to be n choose k equals to n factorial over k factorial times n minus k factorial, like that. So this equals to 1 over n factorial summation. This is going to be n, k equals 0. This is going to be n factorial over k factorial n minus k factorial. Let's just double check one more time. Yeah, that's correct. And now this is going to be f of k of x, and then g n k of x, like that. Yeah, also, yeah, I forgot to include here. So this is the this is at x equals 0. I mean at x equals to x naught or x0, so let's put x0 at every single one of these derivatives like that. Yeah, let's just keep going further. So this is going to be like that, x naught, like that. So that's what we have. And also this is just 1 over n factorial. That's just a constant for whatever the value of n is, and then we can multiply that inside here as per the earlier theorem when we were adding and subtracting series just like polynomials. So you could just take this constant, multiply it inside as per the earlier theorem from our earlier video. So we'll just keep going further. So that means, notice what happens here. This just cancels. So this one, you can multiply that inside. This would cancel with this one here. So now we're just going to be left with this k and this n minus k factorial at the bottom. Yeah, so this is just put a bracket. And now what I'll do is I'll write this one under this one, and then this n minus k under this one, so that matches the k, and this n minus k. So in other words, this is going to equal to summation. This is going to be up to n from k equals to 0. Now we're going to have a f of k, and then this is going to be x naught over k factorial. And now this is going to be times g, the n minus k derivative at x equals 0. This is going to be over n minus k, like that, factorial. All right, and now notice what we have here. This is the kth derivative of f divided by k factorial, and this is at x naught. And this one is the n minus k for the g one. But let's just scroll up. This is just the Taylor coefficients for our f and g functions. For example, let's just scroll back up. Let's keep scrolling. So first of all, this one here, for the multiplication, when you multiply these together, you get our Cn like that. So that's what we have, the power series, and its Taylor coefficient number is just 1 over n factorial times the derivative at the nth derivative, whatever this factorial is. So whatever the n value is at x equals x naught. And in this case, the product is f of x times g of x. But for these individual ones, individual ones right here, so this an, the coefficient, Taylor coefficient is just going to be the nth derivative of f of x at x equals to x naught divided by n factorial. Yes, in other words, that's just the coefficient, an. And we can scroll back up, just to go up to our Taylor series, just to show that formula again. So yeah, this is the Taylor coefficients. So there's a Taylor coefficient, it's just the nth derivative at a divided by n factorial. So, in other words, we already know that. Yeah, so that in our case, we know that it's going to be for f of x and g of x, because we have the nth derivative for the f of x divided by n factorial. And this one here is just going to be, instead of the nth derivative, it's going to be the n minus kth derivative. So let's scroll back here. This is just the Taylor coefficients. So this one right here, now let's put this like this. This equals to, this is a k. This one's going to be called b n minus k. Because remember, those are just the coefficients, so a and b. Yeah, so let's scroll back up. A and b. It's going to be at the k value there. Because we have this k factorial there, and this is the kth derivative, this is n minus k. And this one right here, I'll just put these like this. These are just Taylor coefficients. Taylor coefficients of f of x and g of x. Yeah, so thus what we have is, well, this is just the Cn. So let's just put this down here. This is going to equal to Cn is equal to, and the summation of this is k equals 0, and this is n, and these are just the coefficients. So ak, and this is b n minus k. And let's just box this out like that. So so the coefficients of the multiplication or the product of the two series is just going to be, well, just the a result of this summation of the product of the coefficients of the earlier f of x and g of x series. And so this summation, or this formula, is often referred to as, or called, the quote convolution of an, or a sub n, and b sub n. These are again just the coefficients of the g of x and f of x and g of x series. And this term refers to the result and process of computing it. The word, quote, convolute means to twist or make complex. So basically, you take these two coefficients, and then you make this this process of making it more complicated, or just combining the two, and then you get this third one, this third coefficient, or a sequence of coefficients. You're going to have C0, C1, C2, etc. So anyway, so thus our Taylor series becomes, let's just put this all together. And remember, this is just the coefficients of our series, where we have it is here. So fx times g of x equals to the summation n equals 0 to infinity of cn times x minus x naught in power of n. And the radius of convergence is x minus x naught is less than r. So let's write this all down. So thus this becomes, and we just write it down, f of x, f of x like that, and then g of x, this equals to the summation up to infinity, and this is going to be, let's write this infinity a bit better. So infinity, n equals 0, and now we're going to have a second summation. This is up to the n. So this coefficient depends on the value of n. So we're going to have a second summation like that. Let's put a bracket around there. This is going to be from k equals 0 up to n, and then this is going to be a k b n minus k. Bracket that, and this is going to be our x minus x naught power of n. Like that. And let's just double check this as well. So this is our convolution formula. The Cn becomes this, and our other formula, just the series, is this: fx times g of x equals this, x minus x naught power of n, like that. And now this result, note that this is exactly what we would obtain by formally multiplying the two series out term by term, as we would polynomials. For example, if we had our original just multiplication, so f of x times g of x like this, if we just took them formally both and just multiply them all out like polynomials, we're going to get this exact result. And I'll just do this brute force just to show you. So if we have the first series, n equals 0 up to infinity, the summation, this is the fx formula right here. So an x minus x naught power of n. So let's just multiply these two series out. So this is going to be times it by the summation up to infinity. This is n equals 0. This is bn for the g of x. X minus x naught to the power of n, like that. So let's just say we multiply these out term by term, just like we would polynomials. So this is going to equal to, we're going to read, we're going to need a lot of space. This equals to a naught is the first one. So this is, let's just write this all out. So a naught, and then this is going to be x minus x 0. Well, it's x minus x x naught to the power of 0. That's just one. Let's just ignore that part. And then this is going to be plus a1, and then x minus x0 a1 plus a2 x minus x naught 2, and then plus dot 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 plus, and then we're going to get all the way to the n. But remember, this goes to infinity though, so we just keep going. So x minus x naught, this is going to be n, and then plus dot dot dot, and it keeps going on and on forever. So that's what we have there, and we're going to be multiplying it by, put a dot like that for multiplication. So multiplying it by, then the next one's going to be b0 plus b1. So remember, it's exactly the same thing, but just have the different coefficients. x0, 1 plus b2 x minus x0, 2, and then plus dot 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 plus bn x minus x0, and then this is going to be plus dot dot dot, and then put a bracket like that. Alright, so now we could just do our polynomial multiplication, and now let's just scroll up to see that again, just a refresher, and scroll up. So this is that's polynomial long division, but yeah, here's the so you just multiply each term out. So you multiply this x by this x plus 5, so each single one, and add them all up. Then you do the same for the 3 and so on. So let's just see what happens. Let's just see the pattern that arises. So we'll multiply this a0 just because we have this formula that goes from ak bn minus k. You could also reverse them as well as per binomial coefficients. It just doesn't matter which order you do. So anyways, let's just do this. So a0, we're going to multiply this by this, and then multiply by this, and then multiply by this, etc. Then all the way to the end. Yeah, so we can do that for every single one. Alright, so let's see what we get. So we're going to get a equals to a0, b0. That's the first term. That's just a0 times b0. Then we have a0, b1. And we're going to have this x minus x naught like that, to the power of 1. The next one's going to be, well, a0, b2. And then, yeah, this is going to be x minus x naught, power of 2, plus, and the next one's going to be dot, 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 plus a0, bn, and then x minus x0, power of n. And, yeah, the next one is going to be, well, plus dot, dot, dot. So it just keeps going on and on. You can see the pattern. And then, so that's the first one we're multiplying it by. And then after that, let's just draw this in red. Next one's going to be, well, from, now we're going to multiply this side over to this side. And so on. And then this goes across like that, and so on. So then we're going to multiply that one, and then after that is a different one, and so on. So let's just write this down in black. So this is going to be a1, but now we're writing it, yeah, a1 times b0, but now this power is x to the 1. So we're going to line it up with this one right here. So we're going to line up like terms, just like polynomials. It's going to be plus a1 b0, and then this is going to be x minus x0 power of 1. And then the next one right here, when you multiply this one here, it's going to be a1 b1, but now these powers add up, so it's going to be power of 2. So it's going to be plus a1 b1, and then it's going to be x, yeah, this is going to be x minus x0 power of 2. So just line those up. Then plus dot, 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 plus, yeah, plus eventually we get all the way to this one. Instead of n, it's going to be, because we're adding the one up, so we have to go n minus 1. Which, yeah, so n minus 1 times it by this, with a power of 1, then it adds up to power of n. So that means this one's just a1. So this one's going to be bn minus 1. Because remember, each one of these, this is going to be b2, then it goes b1. b1, b0, this one's bn, bn minus 1. It's going to be x, just the power of n. Because you're going to multiply the n minus 1 term with this 1, so it becomes n. Just as we are multiplying this this power of 1 with this power of 1, this b1 becomes over here. So it's x minus 2, x minus x naught power of 2, plus dot, dot, dot. And then let's do one more, and then you'll see the pattern. It should be pretty straightforward. One more or a few more, but let's just do one more. So now the next one's going to be, now we're going to multiply this a2. Let's draw this in green, or in blue. Actually, let's draw it in green just because different contrast. So multiply it over there, then over here, etc. So, and then we keep going on and on. Let's erase this. Yeah, so now what we have is, this is power of 2, so we need to line it up with this because we're multiplying it by this b0, and so we have to line it up all the way with this one. So it's going to be a2 and then b0. This is going to be plus a2 and then b0. And so on. It's going to be x minus x0 power of 2, and then etc. It's going to be the exact same pattern all the way across. And now we're going to have a, notice that this one goes to b2. Yeah, b2 and b1, b0s, a0, a1, a2, etc. This is going to be now plus this next one's going to be, yeah, it's always going to be a2 because you're multiplying this a2 out by every single one. And then this one's going to be the b minus 2, bn minus 2. Goes to x minus x0 power of n, like that, plus dot, dot, dot. And then yeah, notice what we have here. So we have this is adding up like that. Then eventually you're going to have, it's going to go somewhere all the way across here. It's going to go, let's just draw dot, dot, dot. And this is going to eventually become a n, and then bn minus, or just b0, bn minus n, which is just 0. I'll just write this as b0, or just yeah, so I'll just write it like this, n minus n, which is just 0. So that's just b0, or I'll just remove that. Yeah, it's pretty obvious. It's gonna be 0. It's gonna be x minus x0 power of n, and then plus dot, dot, dot. Yeah, so in other words, for a generic term right here, I'm just going to circle all this out like that, or better yet, draw it in red. So let's draw it in red like that. So this term right there, this is just, let's put this like that. This is just over here. This is just a summation, or let's put it somewhere across here. So this is just summation. Let's write a bit neater. Summation up to n, and then we're going to start off from k equals 0, so that this is ak is 0. This is going to be ak b n minus k, like that. And yeah, this is exactly what we have. This is exactly what we got from our above formula, using the Leibniz rule and then getting it over to this. So this is exactly our coefficients for the multiplication product. And it's the same thing as if you were to multiply it by like just exactly like polynomials, and then for each term you would add these up. So it's basically going to be x minus x0 to the power of n, and then times it by whatever this is for each term. So for each n value, you're going to have to find a summation for these coefficients. So that's this one here. If n equals to 2, you just sum up to this. If n equals to 1, you sum up to this, like that, and so on. That's why you're going to have, in each term, you're going to have to have a second summation. So that's just what this summation means. So exactly the same thing. It's actually pretty amazing stuff. And yeah, this deserves a hashtag amazing. This is pretty epic stuff if you stop and think about it. Alright, continuing further. So also, yeah, for completeness, we can write the multiplication in 3 ways, or the multiplication of the series. So let's just write it in the first way. It's just the summation of the two multiplied by each other. So f of x times g of x is equal to, you can just write this in the first way, summation n equals 0 to infinity of an coefficients, and then this is going to be x minus x naught power of n, times it by, now this the brute force summation like that, infinity. Yes, from n equals 0 to infinity, and this is going to be bn x minus x naught. And now you can also write it as in this way. So if it's let's just write the summation, and now let's say we have when this term is 0, this for this n value is 0 in this case, but then this one isn't. So you're gonna have to when this one isn't, because you're multiplying this into every single one like polynomials. So we're gonna have to just separate these two variables instead of n as both of them equals because you're multiplying it. We're gonna combine them all together and just use different variables. So you can just write it like this: infinity. Let's separate like that. So from I equals to 0 for up to infinity for the first one. And then the second one, we're going to be calling it, just so that it's separate, because we're going to combine them as a double integral, a double summation, but just use different variables so that, we're not using the exact same one like this. Because remember, you can multiply it into itself. So the 0th one here can multiply into the 0, 1, 2, 3, 4, 5th, nth term, etc. in this one. So there's different meaning for it. Yeah, so they're not always the exact same when you're multiplying. So this is going to be from infinity, and we'll call this j equals to 0. This is just going to be ai, and then, so just put this all together. So this one's going to be bj, like that. And then the next one is just going to be, and then these ones, whenever you multiply together, you're going to multiply the powers. You're going to add up the powers. This is the power of n. So if this is the 0th one, if I is equal to 0, j is equal to 1, you're going to have to add them up. It's going to be I plus j, 0 plus 1, for example. So this is going to be x, because you're multiplying it together. When you're multiplying a power, you add them up. So this is going to be, so we're multiplying two numbers, the powers add up. This is going to be I plus j. So, whenever you multiply two numbers of the same base, so x minus x0, and then the powers add up. So that's going to be, you could write it like that, or you could just write it in our format like this. Summation n equals to 0 up to infinity. You just move it down like that, and then this is going to be the summation inside, because this one doesn't go to infinity, it just goes to n, so that's why I just put it like a bracket like that. And this is going to be up to n, so yeah, so this is different because this is going to infinity, these are going to infinity, but this one is going to be within it, so just put it like that so we know. So it's whatever this value is, this depends on it, and this is going to be, from k equals to 0 up to, and this is going to be a k b n minus k, like that, our convolution term, and this is going to be x minus x0 power of n. Alright, so yeah, there's some pretty epic stuff there. So now let's look at an example to illustrate this. So example 1, find the first 4 non-zero terms in the Maclaurin series for e to the x divided by 1 minus x. So recall the table of important Maclaurin series from our earlier video, and we have it over here. So 1 divided by 1 minus x is equal to summation from n equals 0 to infinity of x power of n, in which we get this one. And the radius of convergence is r equals to 1. And that's the term right here. That's the numerator right there. So that's 1 minus x. So, yeah, so we have this 1 divided by 1 minus x. You could consider that as a multiplication of that. So we have this one, and then the e to the x is over here. E to the x is equal to the summation or the series of x power of n divided by n factorial, and we get this. And the radius of convergence is infinity. But since we're multiplying this radius of convergence with infinity and 1 with 1, we have to take the smaller one. So this one is the only one that's defined for both. Otherwise, you're going to be multiplying terms of one of the series not even defined for. So yes, it has to be the other one. So note that when multiplying power series, the resulting series will have the smaller of the two radii of convergence. Otherwise, one of the functions won't be defined during the multiplication. So thus we have this one right here is the e to the x, and this one here is 1 minus x, like that. I mean 1 divided by 1 minus x. So let's write this down. So thus we have e to the x divided by 1 minus x equals to e to the x times it by 1 minus x. Now this equals to the summation, this is up to infinity, from n equals to 0, and e to the x is over here, x to the n, and divided by n factorial. X to the n factorial, like that. And then we're going to multiply this by summation up to infinity, n equals 0, and this is going to be 1 minus x. This is going to be x to the n. And this is 4. We're going to have the radius of convergence is going to be the smaller one, so it's going to be 1. So in other words, absolute value of x is less than 1. Remember, this just means if r equals 1, this just means x minus a is less than 1. That's the same thing, but our a is Maclaurin, so a is 0. So we just write it like that. So absolute value of x is less than 1. And now this equals 2. Let's just write these all out. Write the terms out, or the first few of them. Now let's just write out the first 4. So this equals 2. And this is going to be a bracket like that. This is the e to the x. E to the x is 1 plus x divided by 1 factorial, divided by 2 factorial, divided by 3, etc. This is going to be 1 plus x. This is going to be 1 plus x, and then plus x squared, divided by 2. Remember, 1 factorial is just 1. And 2 factorial is just 2, and then 3 factorial is just 6, so 3 times 2. And this is going to be x3 over 6. Remember, this is just 3 factorial equals 3 times 2 times 1, just 6. Alright, so now this is going to be, that's over there, so plus dot dot dot, and then put a bracket. Now we're going to multiply this out by this one here, 1 plus x squared, etc. So this is going to be 1 plus x squared plus x cubed plus dot dot dot, and that's just going to be like that. And now note that the coefficients of the first one right here, this is just going to be, well, the coefficients are 1, then we have 1 over 1, it's just still 1, this one's 1 over 2. In other words, these are just the 1 over n factorial. So let's write this like this. So the coefficients right here, I'll call this an, the coefficients are equal to just 1 over n factorial. And then this one right here, the coefficients they're all just 1. So this is going to be 1, 1, 1, 1, 1. This is going to be, I'll move it all the way like this, so it matches up with this. This is going to be bn, just to match up with our derivation earlier. Bn equals to 1 for every single one. Alright, so now this entire multiplication, this just equals to, remember our formula, this is the summation up to infinity from n equals to 0, and this is going to be from this second summation. The convolution is up to n, k equals to 0, and this is ak, and this is going to be, so ak, and then this is going to be b n minus k, like that. And this is going to be x minus, this is just x to the power of n. Because remember, this is Maclaurin series, so x0 is equal to x naught is equal to 0. So this can be x to the n, like that. So in other words, this equals 2, and this is exactly, this is going to equal to, the first term is going to be from n equals 0 up to 0. So k equals 0, so it's going to be a 0, and then b 0. 0 minus 0 is just 0. This is going to be like that, and then x to the 0. And then the next one's going to be when n is equal to 1. So we're going to have a 0, and then b is going to n. It's going to be n minus 0. That's just going to be n is 1, so b1. And then plus. Then this goes to a equals to a1, and then b 1 minus 1 is 0. So a1, and then b0. This is x to the 1. And let's do one more, just one more term like that. This is going to be a0 and then b2 plus a1, b1. So it just goes, so this one starts at n and then it goes down 1 by 1. So what is the 2? And this is going to be a2, b0, like that. This is going to be x to the 2. Here I just moved everything to the left, just put dot, 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 like that, and it just keeps going on and on. And remember, these summations are just the same as that polynomials. Remember above here. So this is going to be a0, 0, a0, b0, and then it's a0, b1 plus a1, b1. And then this one's a0, b2, a1, b1, plus a1, b1, plus a2, b0, etc. So just for each single one of these terms. So 2 to the power of 2. So this goes up like that. So the a coefficient goes from the 0th to the 2 to the whatever this was, so the 2. The other one goes from the 2 goes to the 0, etc. So let's just keep going, and now let's just plug this inside. So we know our coefficients. This one is going to be 1 over n factorial, and we already know these ones here. So this is going to be 1, 1, 1 over 2, 1 over 6. This one's just 1, 1, 1, 1, 1. So the first one's going to be 1 times 1. So that's just going to be, it's going to be x0, and x0 is just 1. So just put that everything is just 1. And now the next one, for the this one right here, is going to be a0. a0 we already know is 1. So 1 times b1 is always going to be 1, like that. And then plus a0, a1 is also 1. This one's also, so 1 times 1. It's also 1. So just leave it like that. x1. Plus the next one is going to be a0 is 1, b is always 1. So b is always 1, just leave it like that. And then plus a1 is 1. So a0 is 1, a1 is 1. And then b1 is, b is always 1. So this can be 1 plus a2 is 1 over 2. a2 is 1 over 2. And then b0 is a number, it's always 1. So that's always 1. This is going to be, 1 plus 1 plus 1 half. That's the x2. And now let's go to the next one, which is our power of 3. So that's going to be a0. So it's going to be a0 times the third one. So this is x0, 1, 2, and then 3. And this one's always 1. So this is going to be, again, just 1 plus, and then it's going to be this term, 1 times this one. So so it's going to be 1 times by this coefficient, 1. So the first one is this times this one. And then after that is this. Then after that is this times this one. And then after that is this times this one. For the x power of 3 one. Like that. So just erase these. So it should be pretty straightforward. Anyways, I'm just going in slow motion just to illustrate the point. So this is going to be 1. And the next one is this one times that. It's still going to be 1. Next one's going to be 1 half times it by 1. It's plus 1 half. Next one's going to be 1 over 6 times 1. Like that. And this is x to the 3. Yeah, so we only want the first 4 terms. So that's 4. Plus dot, dot, dot. Alright, let's do a quick calculation of this. This one's going to be 2. This one's going to be, 2 plus 1 half to multiply 2 over 2 here. So we get 4. 4 plus 1 is 5. This equals to 5 over 2. Yeah, this equals to 5 over 2. And this one right here is equal to, 2 plus 1 half. Yeah, we already have that actually. We already have, this is 5 over 2. So this is going to be 5 over 2 plus 1 over 6, like that. And what we can do is multiply the top and bottom by 3 so that they get the 6 denominator. So 3 times 5 is 15, plus 1 is 16. So 16 over 6. And this just equals to, well, divided by 2 on each side, 8 over 3, like that. So our first 4 terms is equal to, and let's just write this down, this equals to 1 plus 2x to the power of 1 plus 5 over 2 x squared, and then plus 8 over 3 x to the cubed, and that's 4 terms, plus dot dot dot, like that. And just for completeness, let's just write 4 absolute value of x is less than 1, so the radius of convergence, like that, and circle this. So there is our answer. Alright, so now that we have that, let's just do a comparison, or just as a comparison, let's multiply just like polynomials and see that, yeah, we get the exact same thing as using that convolution formula. So let's just copy this, just because it's often easier just to multiply directly. So I'll copy this right there. And let's just multiply it exactly like polynomials. Yeah, let's multiply it like polynomials and collect like terms. So the first one's going to be, well, 1 times it across there to each one. And then the next one's going to be the one after. So let's just do the first one first, and then collect like terms. So it's going to be 1 times 1 is 1, plus 1 times x is just x. So we just write exactly the same thing there. X squared plus x cubed, like that, over 6, plus dot dot dot. Then the next one, we're going to multiply the x on every single one, like that. And then the x is going to be, well, 1 times, x times 1 is going to be, well, x. So write this equal to, so that's going to be over here. So it's going to be plus x, like that. And then next one's going to be x squared, x times, x is going to be x squared, plus x squared. Next one's going to be x times, it's going to be x squared over 2. X cubed over 2. Dot, dot, dot. And then let's do the next one, x squared. So x squared times 1 is just x squared. And then the next one's going to be x to the 4. Actually, not x to the 4. X squared times x. That's going to be x cubed plus x cubed. And then plus dot, dot, dot. And the next one here, this x cubed becomes, well, just x cubed plus x cubed, like that. And yeah, this is exactly the same thing as we would get. So there's the 1 there. So the 1 goes down all the way across. This sums up, this sums up, etc. So this equals to 1 plus 2x. So x plus x is just 2x. And the next one is going to be, well, 1/2 plus 2. So this 1/2 plus 2 is exactly the same thing here. This is just 1. Yeah, 1/2 plus 2. So 1/2 plus 1 plus 1 is exactly the same thing. So this just equals to our 5 over 2 x squared. And then this one right here, these all add up. This is going to be 1 over 6. This is going to be 1 over 6 plus 1 over 2 plus 1 and then plus 1. So that's exactly what we had earlier. Plus 8 over 3. x3 plus dot, dot, dot. And again, this is for absolute value of x less than 1. And yeah, so you could do it either or, so check mark. Yeah, so yes, it's often easier just to multiply it exactly like this as opposed to trying to figure out that formula, but it's pretty much the same thing. Yeah, it's exactly the same thing. But yes, visually it's easier just to do like this, but if you're using a computer algorithm or you have a program, yeah, just throw in this formula and you get the exact same answer. Alright, so let's continue further and now look at example 2, and this one is states, find the first 4 terms of the Maclaurin series for sine squared of x. So yes, this is going to be just sine x, yeah, times itself. So you're going to have a multiplication of the same series. So solution, recall from the above table that, let's just scroll up to the table. So we have sine of x equals to the summation from n equals 0 to infinity of -1 to the power of n, and then times it by x to the power of n plus 1 divided by n plus 1 factorial. Yeah, 2 times n plus 1 factorial. And then this just equals to, and you're going to have odd powers, so x to the power of 1 minus x cubed divided by 3 factorial plus 5, plus x to the 5 over 5 factorial, then it's minus. So you're alternating the signs, and you're going by 3, or by odd number in the power and the factorial. So yes, fascinating stuff. And the radius of convergence is infinity. So that means, yeah, so when we're multiplying both the same ones, the radius of convergence is also going to be infinity. So what we have is, what we'll have is, let's just write down the sine series. Sine of x is equal to, and just for completeness, let's just write the entire thing out. This is equals to -1, and then let's see what the power was. Yes, power n. Yes, it's always going to be alternating from positive to negative. And then this is x to the power of 2n plus 1. Let's get the right one, and it goes in odds. So this is going to be the power of n times it by x to the power of 2n plus 1 over 2n plus 1 factorial. So then what we end up gonna have is, or what we end up having is, I'll just move this over here. Let's put equals to, let's put it down here. Is this going to equal to the first one you plug in n equals 0, it just becomes positive 1, and then when you plug in 0, it just becomes odd 1. So x, this one's going to be 1 factorial. It's going to be like that, x, and then the next one's going to be when you plug in 1, becomes negative, and then 1 inside here is going to be the 3. So it's going to be 3 over 3 factorial. And the next one's going to be plus because it's even power, so -1 times -1 is going to be positive 1. Plus, and then this is going to be 2 times 2 is 4, plus 1, so 5. So yes, you can just do it like that, and it's going to be 5 factorial. And then plus, actually not plus, the next one's going to be minus. So that's minus, it's -1 power of 3, so minus, and then it's going to be x to the 7, like that. So yeah, we just want 4 terms, so let's go to 4 terms. Over 7 factorial, and then plus ... And now let's just continue further, simplify this by evaluating these factorials. And here's just a quick calculation check, just because my OneNote, built-in OneNote has calculator, so 3 times, you have 3 factorial is equal to 6. All we do is press equal. 5 factorial is equal to 120. 7 factorial is 504. You have 5,040. So yes, this is going to be just x minus, and then this is going to be minus x cubed over 6, and then plus x to the 5 over 120. Just simplify this further, over 120, and then minus x to the 7 over 5,040, and plus ... Alright, so now that we have this, and also just, this is for all x, or you could just write it as the radius of convergence is infinity, or I'll just be, for x is just an element of all real numbers. In fact, it's also all complex numbers as well, but since I've been dealing with just real numbers, it'd be for all x, so I'll just write it for all x, like this. For all x, like that. Alright, so let's go continue further. So now, thus squaring the above power series and multiplying like polynomials, what we'll end up having is, we're just going to get, sine squared of x. This just equals to, sine x times sine x. So then we're just going to multiply this together, and we're going to get, and here what I'm going to do is I'm just going to copy and paste this. Just paste it right away so it saves some time. So just put it like that, and let's get rid of this thing here. Let's put x like that. So this equals to this, and multiply it by itself. And here, just quickly move it to the left, and let's multiply this again, just to save time in typing. Alright, so that's all we get. We get sine squared of x equals just to this times it by itself. So now we just use polynomial just multiplication, and I'm doing it this way just because, just to start off the other one, and also because it's skipping the, notice that it skips the powers, the x power of 0 skipped, all the even ones are skipped. So we'll just use it this way, and I'll explain after when we do it using the convolution theorem after. So let's just multiply this out. So let's start off with this x, multiply this x over there, and then we multiply each one, and then we do the next one, and so on. So this equals to x times x is x squared, and so we just add an x every single one. This is going to be x squared, x to the 5 over 6. Minus, this is going to be plus x to the 7 over 120, and then this is going to be minus x to the 9. Actually, whoops, I thought this was x squared. No, this is x to the 4. So x3 times x, yes, x3, and this one's going to be x to the 6, and this one's going to be x to the 8. So we just add 1 power because you're multiplying the x there. This is going to be 5040. And then next one, we're going to multiply this 6 inside. This this negative 1 over 6 times x cubed. And that one's going to multiply over to this one. It becomes x to the power 4. So we line it up with this. And it's going to be negative. So we're going to do a negative. Yeah, negative, and this will be x to the 6, so that's multiplying by the x, so this is going to be x to the 4, and then negative 6, just like that. Yeah, negative 1 over 6. And then next one, we're going to multiply by this one. That's going to be 6, and negatives cancel, becomes positive, x to the 6, and then this can be 1 over 36, like that. So 36. And now the next one is the, multiplied by this 120. So 6 times 120, that is 6 times 120, but first let's just write this out. So negative x cubed times x5 is going to be negative x to the 8. And now we have a 6 times 120. Well, what is 6 times 120? That is just 6 times 120 is equal to, well, 6 times 100. Yeah, it goes 6 times 100 plus 2 times, or 20 times 6, or actually just write it out like this. Just do it long way. 120 times 6 is equal to 0. And then 2 times 6 is 12. Add the 1. This is going to be 6 times that, 720. So this is going to be 720 over there. Put a little bubble inside. Or I'll just leave it out like that. Okay, so anyways, we calculated that. So that's 720, and I'll add that in the calculations check in a bit. So, and this is, this keeps going on forever. So plus dot dot dot, plus dot dot dot, and goes on and on. Plus or minus, doesn't matter. And then the next one is this right there. So 120, or this x to the 5 times x, that becomes x to the 6. So this is going to be plus x to the 6, and then just over 120. 120. And then the next one is this over here. So x to the 5 times x, negative x to the 3. That's going to be negative x to the 8. And then over 6 times 120, that we already know that's 720. Like that, and then plus dot dot dot. And then one more term is this one right here. Negative x to the 7 divided by 5040. This one here multiplied by the x just becomes negative x8. It's negative x8 over 5040, and plus dot dot dot, another dot. So what we end up getting is sum this all up, and then this one goes down, this goes down, this goes down, etc. We get a x, and then this one is negative 1 over 6 plus 1 over 6. 1 over 6 plus 1 over 6. And then the next one is plus, actually no, then we need to add the x to the 4. X to the 4, and then the next one's going to be plus x to the 6. This is going to be x to the 6, it's going to be 120 plus 1 over 36 plus 1 over 120. This is x to the 6. And then, we need more room, so this is going to be plus. The next one's going to be this 5041. So this is going to be negative, this is going to be minus. And this is going to be x to the 8. So we'll write this all out. And take out the negatives, it becomes all positive now. This is going to be 1 over 540. Or 1 over 5040. Like that. Alright. And then plus 1 over 720. Plus 1 over 720, plus 1 over 5040, like that. This is going to be x to the 8. And then plus dot dot dot. And just put an equal sign like that, equals all this. Alright, so now that we have this, just put equal sign there, and this is plus dot dot dot, like that. And now we just got to simplify this these fractions. So let's just do some more algebra. So let's erase this. Alright. So I'll just write algebra. Whoops, spelled that wrong. Algebra. Alright, so we're going to have this 1 over 6 plus 1 over 6. Simplify this just for algebra fun. 1 over 6 plus 1 over 6 is equal to, well, 2 over 6. And then simplify that, 1 over 3. So those just add up, and then the 2, goes into 6 3 times. So that's 1 over 3. So circle this. That's the first one. Like that. And then the next one's 120 plus 1 over 36, and so on. So that's number 1 there. So, or just leave it like that. Now the next one, is going to be 1 over 120 plus 1 over 36 plus 1 over 120. That's just going to be, well, 2 over 120 plus 1 over 36. Let's simplify this further. This 2 over 120 is equal to, well, 1 over 60, because just split that up. Equals 1 over 60 plus 1 over 36. And now what we're going to do is multiply the top and bottom to get the same denominator. So 60 over 60 here. This one's 36 over 36. So then this equals 2, and this equals to 36 plus 60. And then the other one is 60 times 36. We can calculate that one up, or I'll just scroll down here. Calculations check, just put it here. So we have the 6 times 120 just from earlier. And then the next one's going to be, let's do 60. Whoops. Yeah, just remove this bold. This is going to be 60 times 36. This equals 2, equals, I don't know why it's not calculating. Alright, let's try that again. I don't know why it wasn't. Let's go 60 times 36 equals, yeah, 21060. Yeah, just put it like that. Just to save time, because it would be a lot of calculations. And now this equals 2, and also 36 plus 60. That is just going to be 96. So, yeah, 60, I just add up 96, 2160. Like that. And I'm going to put this separate. So that next one's going to be like that. So now what we can do here, 2160 divided by 96 goes into, divided by 96 equals to 22.5. Which is, just a fraction like that. Or a decimal place. But now if you multiply that by 2 is 45. What that means is, this just means equals to 1 over 22.5. Which equals to 2 over 45. So we simplified it over to this and circle that. Like that. Because remember, all we're doing is just flipping this one. 2,160 divided by 96 becomes, 1 over 22.5. And so on. So yes. Alright, so now the next one. Let's keep going further. And the next one's going to be this right here. So 1 over 540 plus 1 over 720 plus 1 over 720, then is 1 over 540. So that's going to be, well, 2 over 540 plus 2 over 720. And now this simplifies further into, we'll just take out the 2, split them up into half. So this is going to be 1 over, it's going to be 2,000, and then 520. Because remember, 25 times 2 is 50. So just add another 520 like that. And then I'm just going to move some spacing there. So 1 over 720 divided by 2 is just 360. Or 360, 720. And so on. And then this is going to be, now we're going to multiply top and bottom to get the same common denominator. 2520, 2520 on this side. And then times it by 360 over 360. This equals 2. And this equals 2. The top's going to be 360 plus 2520. Divide this by, and then now we got to multiply these out. And that's going to be, let's get our trusty calculations check. And this is going to be over here. 2520, 2520 times 360, that equals to 9,000. Yeah, let's go here. 90,720, 7200. So let's write this one out. It's going to be there's 900,000. 900,007, and then 200. Like that. And then those add up equals 360 plus 2520, press space equals to 2880. So this equals to 2880 over 97,200. And now getting back to our trusty calculator. So now if we go 907,000, put a comma to see better. And then 907,200 divided by 2880 or 2,880. This equals to space 315. So that's just the inversion of this. So in other words, this is equals to 1 over that inversion. 315. So now we got these all there. Those were our calculations check. Yeah, so this all looks all well and good. So now let's put it all together and then just get our answer. So that is sine squared of x is going to be x, and then minus Here's b1 over 3, and becomes 2 over 45, and then 1 over 315. So yes, let's keep going. So putting it all together, we have sine squared of x is equal to x, and then minus, the first one was a minus, well, this is going to be 1 over 3. 1 over 3, yeah, 1 over 3, this is going to be x to the 4, because remember that's just, yeah, x to the 4, then x to the 6. It's going to be plus 2 over 45. Plus 2 over 45, x to the 6. And yeah, I forgot a mistake the whole time. So this is x squared. So this one right here, I forgot to square it. So this is x times x is x squared. Actually, no, we already have that. That's the x squared there. That just goes down as x squared, like that. So yeah, we already have that correct. And that's just, yeah, x squared. And the next one's going to be minus, and then this part right here is going to be our 1 over 315. So minus 1 over 315. And this is going to be x to the 8 plus dot, 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 like that. And this is for all x. All x. Like that, and circle this whole thing. Over here, I just fixed up that box. Yeah, so yeah, this looks all pretty good. So now note that if we had used our derived quote convolution or convolution formula, we would have to account for the quote 0 terms. And yeah, so we could let's just do that to show you the difference. And so let's just scroll up here. So this was the function, or this was the series right there. So let's use the other derived formula. So sine x like that. This is going to be, so sine of x. Type that a bit better. It's not working. Okay. Oh, there you go. Okay, it's working now. So sine of x, we have to account for. I'm just going to copy and paste that other side there. So this is going to be equal to over here. And so we need to account for the zeros. Yes, we need to account for the 0 terms. So what we'll do is, well, what I mean by that is, this is x to the 1, but we need to, because we derived it for the x to the 0. So this equals to, and the coefficient was 0. So 0 times x to the 0. And then we have plus x. And then minus, or just plus, x to the 0, x to the 2. Or the 0 coefficient times it by x to the 2. And then we have this x to the 3, like that. 6. And then this is going to be plus another 0. All the evens are 0. Etc. And then it keeps going on. And this is, next one's going to be, yeah, the next one's going to be plus x to the 5 over 120. And then it goes plus dot, dot, dot. Like that. So yeah, we have all the zeros at the even. So 0 times x to the 0. Plus this one's 0 times x to the squared. This one's 0, x to the 4. Yeah, so what we have now is these are the coefficients. This is going to be our a0, b0 at this part. And then this one here is going to be our a1 and b1. They're the exact same one because this is the same series. We're just squaring itself. This one's going to be a2 and b2, both the same thing. So anyway, so now if we're using our convolution formula, this is going to be now, so thus, let's put a thus, like that. Thus we have sine squared of x. This equals to, well, the first one we know that's just going to be a0, b0. And then this is going to be x to the 0. And again, scrolling back up to the earlier example, we ended up having this one here. So this is a convolution formula. We get a0, b0, x to the 0. Then we have a0, b1, and then a1, b0. And then this one's going to be a0, b2. Because remember, this is 2, that's the power of 2. And then this one goes, the b's go down, the a's go up. And so on. So this one's going to be, let's scroll up. And a0 times b0, that's just 0 times 0. Yeah, this is just 0 times 0. Just put that as 0, like that. This whole thing goes to 0, both of them. And then the next one is going to be, well, our a0 times b1. Plus, and then a1, b1. And this is to the x to the 1 power. And again, we know this one is a1, b1 are 1. But a0 is still 0. And b0 is still 0. Oh, this is the b0. Like that. So this goes to 0 as well. And then the next one's going to be, well, the next one's going to be a0, b2. Well, we'll just multiply that out right now. So this is going to be 0, a0 times b2 is 0. So that's a 0. And then plus a1 times it by, well, b1, which is 1. So plus 1, and then plus, the next one's going to be, this is going to be a0, and then times it by b0. So 0 times 0. Like that. That's going to be our x2, and then the next one's going to be, this is going to be a0. Again, it's always going to be 0, the first one. And then times it by, this is going to be times it by negative 1 over 6. That's a 3, but it's still 0, so just leave it at 0. Next one's going to be a1 is 1, times it by b2, which is 0. Yeah, so let's put this as 0. And then the next one's going to be right here, a2 is 0, times it by b1 is over here. Yeah, which is 1, but again, we had that a2 is 0, so this would be 0. Then lastly, a3 is negative 1 over 6, but then b0 is 0, so this is b0. And this is the x cubed, so that's why this one vanishes. And then the next one, the next non-zero we're gonna have now is the x to the 4. So the x to the 4, so we have 0 times 0, so a0 times b4 is 0, plus a1, which is 1, times it by, this one here is b3. This is going to be negative 1 over 6. This is going to be 1 times negative, or just put a negative now. 1 times that is going to be negative 1 over 6. Yeah, and then the next one's going to be right here, a2, which is 0. So just plus a2 is 0, and then times it by b2 is also 0. And the next one's going to be negative 1 over 6, times it by, this one's b1, is 1. And then the next one's going to be over here 0, and then times it by 0. Yeah, this is going to be our x to the 4. And so on. So yeah, this is going to be our x to the 4, and that means, well, and then the next one is going to be plus dot dot dot, etc. I'll just leave it like this. So this one vanishes. So this equals to 0 is 0 plus 0. This one is, now we have a 1. So it's going to be an x squared, and the next one's going to be, take this out, this negative, we get negative 1 over 6 plus 1 over 6, etc. And this is x to the 4 plus dot dot dot. And we're going to get the exact same thing as this one here. So we get over here, yes, this is going to be x squared minus 1 over 3. That's just our 1 over 6 plus 1 over 6. Because remember, yeah, we get it all the way here. So this is the part here. And then if you keep going, you're going to get eventually a 120, a 1 divided by 120 plus 1 over 3, 6, etc. And you can see the symmetry as well. And these ones just have the zeros ignored. So yes, fascinating stuff. So I'll just square this. And just put a check mark. Yeah, it checks out. Alright, so yes, we got that sorted, so that's fascinating stuff. So now, continuing further, let's now look at division of power series. So the earlier lecture PDF didn't go over division of power series in any detail besides just an example, but I was able to figure out how the proof is derived from Wikipedia, and this is from the power series link there, or the page. So, and from it, what it would state, it was, again, so starting again with our previous power series F and G, we can define a power series as the division of the two. So if we're given if we have fx equals 2, this is just a summation up to infinity from n equals 0, and this is our an, the coefficient, x minus x0, and this is to the n, power of n, and then we have our g of x is equal to summation n equals to 0, and this is going to be our bn, x to the x0 to the n, like that. And we're given that both of these radius and convergence are the same, so x minus x0 less than r, like that. Alright, so we have this. So now what we're going to do is we're going to define, because we have that, we're going to define another power series as the division of the two. Yeah, here we'll define f of f over x, f of x over divided by g of x equals 2, and now just this this series divided by this series, like that. Infinity up to n equals 0, and this is an x minus x naught power of n. Divide this by, this is going to be infinity, n equals to 0, and this is going to be our bn x minus x naught power of n. And now this equals to, we're defining it as equaling to a series, another power series, with the coefficients are going to be now dn. D sub n, like that. X minus x naught power of n. Alright, so just moved it over here. So now if we define it like this means that, well, we should be able to just move this over to that side. So we just move it all the way to that side. Put a better like that. So in other words, we're going to multiply this out over to this side. So then that means, yeah, when we multiply this out, this is just same as multiplying g of x out of there. Then what we have is, then what we get is f of x, because we're multiplying g of x out on both sides. Just multiply g of x, get rid of it. So this cancels, goes over to here. So f of x is going to equal to, well, we already know f of x is equal to this, and now it's going to equal to this newly defined series times it by g of x. So this is going to be equal to, and let's put the g of x one in front of this one. So this equals to, I'll put it like this for completeness, g of x times it by whatever that one is. Well, yeah, let's leave it like that. Just move it out. This is going to be equal to, like that, n equals to infinity. This is going to be our bn of x. This one is just our g of x times it by, now we have this. So we basically turned a division into a multiplication. Yeah, just keep finishing up. So n equals 0 up to infinity, and this is our dn, the one we defined, the division, x minus x0 power of n. So in other words, we've converted this division definition into a multiplication, like that. So now this is what we have, and where we know f of x, that's what we're given, and we know this one is just g of x, so now we just gotta solve this one somehow. Yeah, and that somehow is recursively, yeah, so we can now just quote recursively or repetitively / procedurally solve for the terms dn, so these coefficients of this division that we defined, and yes, we just solve that, and that is the polynomial long division format. So for division, we have to ensure that g of x is not equal to 0, because you're dividing by g of x here, so you can't have it divide by 0. That's not defined, goes to infinity. And also have to be mindful of mindful that there may be points where g of x is equal to 0 inside the region of convergence. Yeah, so we're given a region of convergence for f and g of x, but it does not state if it's 0 or not, because it can still be 0 and still be within the radius of the convergence. So we have to ensure that it's not equal to 0 in our domain when we're looking at it. And also, after thinking it over, and I actually had to insert this little clip in this video, so you might, if you see the rest of this video, you might be seeing the old notes in this little segment. So I had to just change it up, because after thinking it over, I'm not too sure what to make of my calculus book's earlier statement, which states, as I showed above, for division we require b naught is not equal to 0, and the resulting series converges for sufficiently small absolute value of x. This one is the one I'm not fully sure on this, or even the sufficiently small one there. I'll have to look at it in future, but because I'm pretty certain that all you need to do is, if for the region, you have to ensure that g of x not equal to 0. So that's that's the only case. You see, you're not dividing by 0 there. So yeah, I just wanted to I had to pause the video, and I finished the video, and then I had to look at this again, so cut it, put this back in. So anyways, since we are effectively solving for a power series that can multiply, that can multiply with g of x to obtain f of x, that's right here. So this is a power series. We just multiplied this g of x to get this f of x. Remember, that's just g of x at the bottom, bn there, bn x minus x naught power of n, the series. Yeah, we can just do the inverse of multiplication of polynomials, that is division, just as with polynomials. So if this is the multiplication to get this f of x, we can do the inverse and do long division. Long division to get to this part right here. So we could do long division of these two and get to this part right here. And so basically we just gotta find these coefficients, and using polynomial long division, as I'll go over here, and then I'll also later prove using multiplication to get back to our result, which is pretty fascinating stuff. Or let's keep going further. So example 3, so given the following power series for hyperbolic sine, determine the power series for hyperbolic cosecant. And so this is what we're given in a lecture PDF. So sinh, it's pronounced sinh of x, hyperbolic sine, is equal to x plus x cubed divided by 3 factorial, then plus x5 divided by 5 factorial, plus x to the 7 divided by 7 factorial. So it's exactly the same as the earlier function, let's see the earlier multiplication, or let's go to that table. So it was exact same one as exact same one as this. Actually, no, it was the exact same as the I'll go back here. Exact same as a sign, except it's all positive. So instead of this x minus x cubed over 3 factorial plus x5 is always going to be positive, like that. So let's keep going here. And let's see what we're also given. Oh yes, I also forgot to state here. So the radius of convergence is infinity. So this is infinity. So this is for all x, or just radius of convergence is infinity, like that. All right, so let's continue further. So solution. Recall that hyperbolic cosecant is just or spelled like this, csch, is just 1 over sinh. Thus, we can set up our polynomial long division as follows. And this is just this power series. We're going to divide this. We're going to divide 1 by this power series. So let's write this down. So hyperbolic cosecant of x is equal to 1 over sinh of x. So in other words, we're going to be dividing this entire thing by 1. So 1 over, and let's put this whole thing in. So x plus x to the 3 over 3 factorial. That is just 3 times 2 is 6. We already solved this one. And then x to the 5. This is going to be x to the 5 over. And we already know what 5 factorial is. That's just 120. And then the x to the 7, that is... that one is, we already know that. That is 5040. It's going to be x to the 7. We'll go plus dot dot dot. This is going to be 50, 40. And remember, we already solved that. Let's go back to that earlier calculations check. See, scroll all the way up. So so we already have that. So 3 factorial equals 6, 5 factorial equals 120, and 7 factorial is 50, 40. So we already have that. So, and now we're going to be dividing this whole thing up. Alright, let's put this here. So we're going to divide this out. So we're going to have to set up our polynomial long division. Let's just follow the polynomial long division for this power series. So let's scroll up again to illustrate how we go about doing that again. Scroll all the way up, and this was right here. So the polynomial long division. So if we're dividing, for example, here, this function divided by x plus 1. So we would put that function on here, and then we would put the denominator goes here, and then we would find 1 and multiply it, etc. So let's just do that here. So in our case, the denominator is the power series, and the numerator is just the number 1. So this equals 2. This equals 2, and this is going to be another long algebra session. So I'll write it like this. I'll put it in the middle. So we're going to put it like this. The first number is 1. Make this a bit bigger so it doesn't look like a 1. So like that. And then the ones on the, we're going to put this thing on the left side. So let's put it all there. Let's put it all there. Copy and paste. And throw this down here. Alright, so we have that here. Let's make it a bit smaller. Alright, so now what we'll do is multiply this x to match up with this 1. So to do that, we need to do a 1 over x. So 1 over x times x equals to 1. Like that. And then we have to do that to every single one. So we multiply this by every single one there. So now we'll multiply this 1 over x times x cubed over 6. It just becomes plus x squared over 6. Like that. And then the next one is going to be, let's put it 1 like that. And then the next one is over here. And let's just do 4 terms. So this is going to be x to the 4. So we just subtract 1 there of the power, 120. And then one more, x to the 6. 50, 40. Like that. And then we subtract. Like this. Subtract it. And this one here, these ones all just have a 0, 0, 0. So we're all subtracting. So we're just subtracting nothing from it. 0 from it. So this one's going to be 0. So we're going to be, this one vanishes. And now this one here is going to be negative x squared over 6. Negative x 4, 120. And then negative x 6. And again, just put a plus dot 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 to indicate it keeps going on forever. But the first few terms are the most important ones. Plus 0, plus dot dot dot. Or actually this one's would be plus minus dot dot dot. So minus dot 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 like that. And now the next one, well, we got to multiply this x by something to get this negative x squared. negative x squared over 6. So that's going to be, well, just negative x over 6. So that the power just add up becomes this. So this becomes minus, multiplied by x, is going to be negative as x squared over 6. And now we multiplied inside each one of those. This is going to be negative x to the 4. And now this is going to be a 36. And yeah, keep going. So negative x times this one here, 5. That's going to be negative x to the 6. Notice that these all line up. And yeah, so we are lining them up. Yeah, so these all line up like that. And then 126 times 120. Remember, that's just already, we know that's 720. Like that. And then the next one's going to be, well, minus as well. So you can see the pattern. And now we just subtract. Yeah, so subtract this whole thing. We're going to do a subtract like that. Just put it out there, and etc. Put a bracket, and put a bracket. Just to indicate we're subtracting. Just put a bracket, so subtracting the whole thing. So this is going to be, these ones vanish, so there's going to be a 0 there. And then the next one's going to be, this one subtracted by this. That's the same as adding it. Yeah, and this 0, just remove that 0. So this one here, this is going to be, well, we're going to have to do some algebra. So, yeah, so let's do some algebra here. This is going to be negative 120. I mean, negative 1 over 20. Yeah, negative 1 over 120, and then minus this one here, that's minus a negative as a plus 1 over 36. Like that. I'll make some room. Plus 1 over 36, and then same common denominator, multiply by 120 over 120. We'll multiply by 36 here, so the same common denominator, over 36. And then what we end up having is, and let's just do some calculation checks. And that's here, so let's add these up first. So this equals to negative 36 plus 120 over, and this one's going to be over here. Calculation check, so negative 36 plus 120, that's just 84. We do space equals 84. And 36 times 120, that's just to get the bottom, the denominator. Let's do the calculation check again. Built-in OneNote calculator, 4320. 4320, and now this equals to, yes, 84 over 4320. 84 over 4320. Let's keep going further, and now what we'll have is, we're going to look at this 84, and if I divide by 84 by 4, or you can do it recursively, like this. This is 43, this is the numerator, that's the denominator, so if you divide by 2, this equals 42, but you can divide it more. This equals to 2160, but you can divide it even more. So we'll divide by 4 the next one, and just see, yeah, 1080, and then this one until it becomes an odd number. Yes, divided by 4 equals 21. So yeah, I was doing that recursively. So you get 21, and then now if you divide 21 by 3, we get 7, and divide this one by 3. Yeah, divided by 3 equals 360. And then, yeah, so now we're stuck there, 7 and 360. So that means, and so now this means is this equals to 7 over 360. Because this was just the inversion of it, and it's just constantly simplifying it there. And this is going to be, when we're adding this up, this is going to be 7, and the signs are taken care of, 7 over 360. And this is x to the 4. And let's put a little bubble inside this one, so that it's calculations. And then now the next one is this negative 140, negative 1 over 5040, and then we have to subtract by this negative, or it's plus 1 over 720. So that's going to be, let's look at this, and let's do another calculation. This is going to be negative 1 over 5040 minus negative 1 over 720. That's going to be plus 1 over 720, like that. And let's move some space again. It's going to be 720 over 720. Just get the same common denominator, and this is going to be, again, just some algebra fun. 720, so we're subtracting a negative, times it by 5040 over 5040. So this equals to, let's put this all together. This is the second calculation. So the negative 720 plus 5040, this equals to 4320, and then 720 times 5040, this equals to 362, yeah, 3,628,800. So let's write this down. This is going to be, let's put them combined together, save some room. 4320 over 36288800. Like that. And then here, if you divide 3628800 by 432, you get the inversion of it, 8040. So in other words, this is equal to 1 over 8040. Alright, yeah, so we have this 1 over 840. So just box this out as well, or just circle it like that. And now this is going to be plus 1 over 840, and this is going to be our x to the 6. And the next one's going to be plus dot dot dot, etc. So we just want 4 terms, dot dot dot, and it keeps going on. And now the next one is, well, we gotta get the we gotta match up the 7 over 360 times x to the 4, and we can do that by, well, this is just gonna be the x, so that's just gonna be x to the 3. So we're gonna have to multiply it by 7 over 360 times by x to the 3. That's the only thing that's gonna be changed is this. X to the 3 becomes, yeah, it becomes x to the 4 there, and then the 7 over 360 fraction is still there. So multiply this by this, it becomes plus 7, yeah, so let's put a 7 over 360, x to the 4, like that. And then the next one is 6 times the bottom there, so 6 times 36. Yeah, at the bottom there's going to be 6 times 360, and there's a 7 there. Let's put a 7 on top. 7 over, because it's here, this is going to be x to the 6, plus dot dot dot, and then the 6 times 360 at the bottom, that's just going to be calculation check. We already did this one before, but just put it here for completeness. So this is equal to 2160. So this is going to be 2160. And now we're going to subtract here, and when we subtract this, subtract this whole thing. By that, this one cancels, and now we're left with this part here, and I'll just put in x to the 6, and now we got to solve this one. So now, let's move this further. Yeah, this one's going to be, now we have this 1 over 840, so I'll put this down like this. 1 over 840, and make some room, it's going to be now minus 7 over 2160, and then just multiply top and bottom. 2160 over 2160. And then this one's going to be minus 7 over 2160 times by 840 over 840 to get the same common denominator. Now this equals 2. Yeah, this equals 2, and then use a trusty calculator. So 2160 minus 7 times 840, this equals 2, well, negative 93. Whoops, no, that's not the, I got it mixed up. This is over here. That's right here. So this is going to be equal to space, negative 3720. It's a negative 3720, and then the bottom is going to be 2160 times 840. So same common denominator, 2160 times 840 equals to, this is 1,814,400. 1814400, like that. Write this a bit better, it's 8. Alright, and now this one here, we could do that exact same thing before. There's the zeros there, so we can divide them out. So again, we could do recursively and divide by 2. Yes, if we divide by 20, you will get a number, then we'll divide it again, 40, so we get negative 93, like this. Same one here, divide by 40, just refracting out the 40 out of there. Comes 45306. Let's move this here just to show you. And this one is again 93, negative 93. And then, yeah, and actually just because we already have the negative sign, we'll just remove this so we don't get confused. Just remove the negative signs because it's already going to be negative. And then the next one, yeah, so this one becomes that. And then we're going to divide this one even further, so divide this by 3 now. It's 93 divided by 3 equals to 31. And likewise, this one here divided by 3, so factor out the 3 like that. Equals to 15120. So in other words, this becomes 31. Now this was all inverted, so this becomes negative 31 over now 15,120. 15,120. So in other words, this becomes right here negative 31 over 15,120. And yeah, so this one box this out like that. And now this one here, the next term is to multiply by x to get to this one. That's just going to be this one, but to the power of 5. This is going to be negative 31 over 15,120, like that, x to the 6, and plus dot dot dot. All right, so we have that, and so this is the first 4 terms there. And then when we multiply it inside there, we get this negative 31, 1520, and then x to the 6, etc. Or I'll just leave that out, because once you multiply it out, yeah, then you have to account for more terms there, etc. So plus dot dot dot. So here's where we left off at. We'll just leave it off at that, and this is the first 4 terms. And yeah, this is actually 1 power less. Yeah, this one should be a 5, not a 6, because this was the 6, and we're multiplying by x. So the power of 5, like that. Alright, so now that we have this, let's put it all together. So let's keep going down here. So thus we have hyperbolic cosecant, or csch, or cosec, I'm not sure how to pronounce this one, equals to 1 over sinh, or hyperbolic sine of x by definition. And this equals to, so yeah, so now this division equals to our polynomial long division format for power series. So 1 over x minus x over 6 minus x over 6. The next one's going to be 7 over 360 x cubed, and then 31 over 15,120. This is going to be, let's see what that was again, 7 over 360. 7 over 360, this is x to the cubed, and then minus 31 over 15,120. 31, 15,120, and this is x to the 5, like that. And then it's going to be plus dot dot dot. All right, here now let's just box this whole thing out. So this is going to be like that. And like that, perfect boxing. All right, so now the next step is, well, we got to find out what the interval for convergence is, because again, we're dividing by this sinh of x, and we have to ensure that's not equal to 0. So to obtain the interval for convergence, we need to ensure that sinh of x is not equal to 0. Recall that the definition of hyperbolic functions, yeah, from my earlier video, so these are just defined basically as functions of this e to the x exponent. Yeah, so looking at our sinh function right here, this is by definition is just equal to is a hyperbolic sine of x equals to e to the x minus e to the negative x, and then all divided by 2. And then again, we already know that the hyperbolic cosecant of x is equal to 1 divided by this right there. So, and if in my earlier video I showed that the graph of it looks something like this. This is sinh of x, and it goes somewhat like that, and it's in between these two halves, 1/2 e to the x, and then minus 1/2 e to the negative x, like that. And the only time it's 0 here in real numbers is when x equals 0. Yeah, so that's the only time it's 0, and it just goes to infinity like that. So in the domain of real numbers, the only time sinh of x is equal to 0, the only time sinh of x equals 0 is at x equal to 0. So thus our interval of convergence is for all real numbers with absolute value of x, not said, of x is greater than 0. Yeah, so that's we can have the interval, yeah, anything greater than that. So anyways, keep going further. So imaginary numbers and Euler's identity. Interestingly, if we consider the domain of all numbers, both real and imaginary, then our domain of convergence will be different. And yeah, because the PDF uses a different domain here. It was accounting for imaginary numbers. So recall the definition of imaginary numbers from my earlier video. So we had imaginary numbers definition: I squared is equal to -1. And then the square root of that would be I equals to square root of -1. Just square root both like that. But here's a side note, which is interesting. Very few bring this up. So a side note: -1 squared is equal to plus or minus I, not just I, because well then when you square it, plus or minus I squared is just equal to I squared, like that. Yeah, so that because this negative sign just goes away, it becomes positive, and this just equals to -1. And also here, yeah, if you can Yeah, if you can square root this one, that's by definition equal to I, but again, it could be negative I as well. Similar to negative 4, positive 4 square root, this just equals to, well, usually people say just 2 because 2 times 2 is 4, but this can also be equal to, or negative 2. Because again, you can do 2 times 2 is equal to 4, or, and here I just moved it over to here, so square root of 4 is equal to 2, or negative 2, since 2 times 2 is equal to 4, since that, and negative 2 times negative 2, and the negatives just cancel, it equals to 4. So yes, so that's something to think about. So there's always an extra figure, and then the question is, how does this change what follows from it? So anyways, keep going further, and I may be going over this in a future. So anyways, note the famous quote Euler's identity, which I've yet to cover in my channel, and it's from Wikipedia. So this is the identity: e to the power of I pi plus 1 is equal to 0. This is a very famous one, but then the question is, what happens if we account for this negative sign, or this negative I? Now that is something to think about. And the YouTube channel Fractal Woman actually was discussing this. Very interesting stuff. So anyways, when accounting for imaginary numbers, our hyperbolic sine function equals 0 whenever x is an integer multiple of pi I. And we can see this by, well, let's write our Euler's identity. So Euler's identity, we could write it as either or. So we can have e to the I pi plus 1 or equals 0, or just move this over to the other side. So e to the I pi equals to negative 1. So when we have that, and then by definition, let's look at our sinh function again. So hyperbolic sine is by definition from our earlier video this, e to the x minus e to the negative x over 2. And then we'll have sinh of x, so sinh of x is equal to e to the x, or e to the positive x, minus e to the negative x over 2. And now whenever x is an integer multiple of pi I, or I pi, what we have is, well, let's just look at what happens when we have that scenario. At x equals to integer multiple n times pi I, where n is equal to 0, plus or minus 1, plus or minus 2, etc. Dot dot dot. These are again just integer multiple, plus or minus integers, doesn't matter. We have sinh of x, or sinh of so x is equal to n pi I equals to, plug this inside, e to the n pi I minus e to the this is going to be again negative n pi I, like that, over 2. And now just using our exponent laws or power laws, we can just factor out this n there. This is the same thing as writing e to the pi I over n, like that. And then minus, this one here is a negative, so you can move that down and do the exact same thing there. So this becomes minus 1 over e to the pi I over n, like that. And this is all divided by 2. And again, the e to the pi I, e to the I pi, or pi I, we already know that. That just equals to Euler's identity right here. This is equals to negative 1. So just move it over, it equals to negative 1. So that means what we get is this equals to negative 1 to power of n minus 1 over negative 1 to power of n, like that. And then again divided by 2. And now what this equals to here is, well, this one right here, this 1 over negative 1 to power of n, it's the same thing as just writing 1 over, the same thing as writing negative 1 to power of n. Yeah, so I'll just put a note. Yeah, this is the same thing. 1 over negative 1 over n equals to negative 1 power of n. Because if the bottom's negative, negative 1, the only absolute value can be is 1, and it's either negative or positive. If the bottom's negative, it's the whole thing's negative. If the top is negative, the whole thing's negative. So this is just equals to negative 1, like that. Yeah, so that's what we have is equals to negative 1 over n minus negative 1 power of n over 2. These just cancel. This equals 0. Yeah, so now that we have all this, so thus for completeness, our power series for hyperbolic cosecant has the following interval of convergence in a domain of all numbers. And let's just write down our whole thing. So we're going to have, yeah, so all numbers, not just real. So real and imaginary. So this is hyperbolic cosecant of x equals to 1 over hyperbolic sinh of x. So just for completeness, this equals to 1 over x minus, see if I can remember it all, 1 over 6x. Plus 7 over 360 x to the 3, and then minus, this is 31 over 15 120. So yes, it's ingrained into my brain. Plus dot dot dot. Let's just double check that quick. So that's over here. So yes, 1 over x, negative x over 6, and then we have a 7 over 360, and then this x cubed minus 31 over 15 120. That 1 is a bit too close. 5 1 2, like that, and 0 there. 5 1 2 0, and then x to the 5. And let's keep going here further. So yeah, so there's a 31, negative 31, and then divided by 15 120. And yeah, this looks all correct. And this is again for number at x equals 0 is g of x is equal to 0. So this is equal to 0 at g of x. No, this is equal to 0. Sinh of x is equal to 0 at x equals 0, and at the integer multiples of pi, or integer multiples of pi I. So basically, we need to ensure that x is never equal to pi, because at the imaginary scale, some of them will be equal to 0, so undefined. So for, and to make the interval of convergence small enough, sufficiently small. Yeah, sufficiently small so that we never have an issue real or imaginary, whether it's equal to 0. So this is gonna be absolute value of x is greater than 0 and less than, yeah, just put pi. So less than pi. So because when it equals to pi, there's gonna be some imaginary imaginary numbers that include or imaginary multiples of this pi, including at n equals to 1, such that it's gonna equal to 0 and thus not defined when we're dividing by this right here, this sinh. So this is put a line like that, and let's box this whole thing like that, and we are boxing it, and it's a good box. Alright, so now that we have all this, yeah, it looks all correct. And now finally, let's just double check our division by multiplication. So yes, so as a double check, we can do polynomial multiplication to get from this hyperbolic cosecant and sinh to our initial numerator equal to 1. Remember, that was our f of x. This was our g of x, and this is our the other function, or the other power series, the division. Remember, this is our f of x is 1. So let's just do that right now. Yeah, so in other words, let's just do this. So we're going to have hyperbolic cosecant of x is equal to 1 over hyperbolic sine of x, or sinh of x, like that. And now what we're going to do is multiply this out over there. So that what we should have is, we should have a 1. Yeah, a 1 equaling to hyperbolic this cosecant of x times by hyperbolic sine of x, like that. So this is what we should have, is we should equal to that. So thus, let's do polynomial long multiplication. So this equals to, let's write this out, hyperbolic cosecant of x times by hyperbolic sine of x. This equals to, and let's just look at our, this is the resulting answer right here. So this is the one we got. Let's just do the first 3 terms like that, just because it's a bit tedious afterwards. So it's going to be 1 over x minus 1 over 6x, and then plus 7 over 360. And here, just move it down over there. So this is going to be, the next one's going to be, well, minus dot dot dot. And then we're going to multiply this by sinh of x. And remember, sinh of x is scrolled all the way back up to what it was. Sinh of x, what we were given. Yeah, so hyperbolic sine of x is just here. So x, then x cubed over 3 factorial, or that's a 6, 120, 50, 40. Like that. And then, yeah, so 7 factorial, and so on. Those are just the odds. Scroll it back here. This is going to be times it by x, and then plus x to the 3 over 3 factorial is 6, and then plus x to the 5 over 5 factorial is 120. And then this is next one's going to be plus x to the 7, and or I'll just leave that one out. Yeah, so just do 3 terms, dot, dot, dot. And then we multiply this out. So we're multiplying this this x inside here, then over here, then over here. So we get equals to x times 1 over x is just 1. And then next one's going to be, well, negative 1 over 6x squared. Next one's going to be, this one here, I forgot to put this as x cubed. Yeah, that's just x cubed. That's just 1 over here. Yeah, that's just this x cubed over there. Anyway, so the next one's going to be x over here is going to be plus 7 over 360. And it's going to be x to the 4. And the next one's going to be, well, minus plus dot, 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 minus dot, dot, dot. And then let's do this one over here. This is x cubed. And the x cubed are multiplying by 1 over x, so we're going to subtract a power there. So it's going to be x squared. So that's going to be, well, plus, this is going to be x squared over 6. Yeah, x squared over 6. Like that. Let's put it like this. Plus 1 over 6x squared. And then the next one's going to be over here. This is going to be multiplied by, it's going to be negative x, this is going to be, yeah, this is going to be x to the 4. Negative 1 over 6 times 1 over 6. And then this is going to be 6 times 6, 36. Like that. And then next one's going to be plus dot, dot, dot. And then let's do one more here. So this x to the 5 over 120 times by 1 over x, that's subtract a power. It's going to be plus x to the 4 over 120, like that, and then plus dot, 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 keeps going on. And notice what we have here. So this one goes down, 1 is down there, so this equals to 1. This one here, these just cancel. So negative 1 over 6 times x squared plus x squared over 6, that just cancels, equals to 0. This goes to here, plus 0. Now this next one right here, this is 7 over 360. And then this one's x over 360. This is 1 over 360. This is 1 over 120. So in other words, let's put that in a bubble right here. 7 over 360 minus x 1 over 360, or 1 over 36. So let's times that by 10. So we have a minus 10 over 360 times 10 on top and bottom. And then this is going to be a plus. This is going to be plus 1 over 120. Times it by 3 on top and bottom, so we get 360. This one's going to be equal to negative 3 over 360. And 120 times 3 is just 360. So this becomes plus 3 over 360. And this just cancels. Like that. So this just equals 0. And this is just 0. And you're going to eventually have the same thing on and on. All of them going to be 0, 0, 0. And yeah, that's just a quick double check. So yes, fascinating stuff. So it just equals to 1. This is what it is expecting. Equals to 1. Like that. And yeah, that was a check mark. There. Let's put a check mark. Hashtag. And this deserves a hashtag magical stuff. And yeah, we are done now. So this is a lot of algebra, a lot of power series. But it's pretty fun. Just get your mind up to speed and follow along logical steps. Anyways, that is all for today. Just put a check mark here. All right, thanks. Yeah, that's all for today. Thanks for watching. And let's scroll up. And like always, you can view these notes in the link in the description below, as well as on the Hive blockchain. And everything is in the description below. I'll put the timestamps as well. I've been starting to do that. It's pretty epic stuff. It also shows on the bottom bar on the YouTube video. It shows you the timestamps. Like you can just move your mouse and scroll and see it. But anyways, let me know what you think, and the timestamps are there, so you can skip through wherever. And you can also play faster speed, and you can skip through the algebra or enjoy the algebra. Very fascinating stuff. And yeah, so this is the proof I got from here, and the Wikipedia one just a bit for the division. Anyways, that is all for today. Let's scroll up, another epic math video. Anyways, thanks for watching, and stay tuned for another math easy solution.